for quality assurance purposes, right? All right. So, what we're going to do today is to start the lecture with something that is going to showcase what you will be doing for the rest of this semester, okay? Not your life, okay? Some of you may actually enjoy it so much that you choose a career to be doing this like for the rest of your life, okay? Yeah, maybe it can happen. All right. So on the left-hand side, we have a C code or C program. And I think most of you should be able to understand the C code on the left-hand side, other than the one little thing called a uint8 underscore t. That is introduced already in this class. Okay, kind of informally, but it had been introduced already. So uint8 underscore t means it is an unsigned A-bit integer. And those names, are type def or type defined by the header file that I'm including, which is standard integer.h. Yes, the font. Yeah, I suppose. Let me view, zoom in, or I can just turn. Zoom in is probably better because I don't want to change the default. So, and then I need to. Okay, let me get out and then come back in, because it's not dividing the screen correctly once I change the font size. Okay, so on the left-hand side, we have the C code. Doesn't do much. This is a function. It adds the two parameters, return the sum of the two parameters, and then we have main, which also doesn't do anything particularly useful. It has a local variable x. It calls sum with two arguments, 4 and 7, and then it stores the result back into x. On the left-hand side, you have something that probably is foreign to you unless you have taken this class before or some other assembly language programming class. But basically, okay, I have to change this to a 4 to match the C code. But that's the assembly code implementation of the C code. So my focus of this class I would say for the last 6 weeks, 5 to 6 weeks or so, is to focus on how do we look at C code and translate that into the equivalent assembly code. And somebody's going to complain and say, this is the job of the compiler. Yes, it really is the job of the compiler, but you need to understand how that works. Okay, what C code translates to what kind of assembly code? Okay, so now our focus is going to be on the assembly code. So what I'll do is I am going to start at the very beginning and go like, okay, let's start with the first instruction. Actually, the first instruction is a no-op instruction. It is mandatory, but we'll start with the first instruction here as LDID with a 0. Okay, it is these are mnemonics, MNEMONIC mnemonic, which means they are really just names of opcode that is easier for us humans to remember. Then you guys go like, LDI does not make sense to me. Well, it stands for load immediate. Okay, now you will encounter these mnemonics a lot more, so there's no need to frantically copy all the mnemonics today. But what we want to focus on is, what are these mnemonics? What do they actually represent? So a mnemonic is essentially a group of letters, okay, typically an abbreviation of some kind, that can remind you of what an opcode is going to do. So a mnemonic is basically a human readable version of an opcode. An opcode is basically a content that lives in RAM, in which case the processor will load into its own register, and then it will execute that opcode. Okay, so are there are there any questions about what I just said? Yep. Mm, no. So okay, so an opcode is a kind of index, but not when it is still living in RAM. It is an index into the ROM. So that part will be clear today when we start to execute opcode. Okay. Yes. So we'll actually see the mechanism of how that happens. Okay. So let me first do one thing. Okay. So I'm going to assemble this program. Okay. So I'm going to let's see. Um, let's see. How do I do this? I'm just going to be lazy and start another one. So I'm just copying that code into my buffer, and then I will use a assembler to do this. Okay, so we'll go like this is, what was the name again? I can't remember my name, the name of my programs. So ex1, there we go, ex1.ttpasm. So ttpasm stands for Text Toy Processor Assembly File. Okay, so that's the abbreviation. So now I'm going to introduce you to the assembler. Okay, the assembler of this class is going to be on a Google Drive. In today's lab instruction, you will learn how to get that. Okay, so there's no need to frantically copy how to get there. So I will basically just navigate to that folder. It is under my drive, under CISP 310, under shared, under processor, and the assembler is simply called the assembler. There we go. And before someone points out to me and go like, tech, that is not an assembler. This is a Google Sheet. It is both. It is a Google Sheets programmed to be an assembler. Okay. Well, it gets the job done. Okay, so don't ask me, why I need to want to do it that way, but it will get the job done. So the way you work on this is you go to the source tab. You can see this is the source tab. And then what you do is you basically paste the code that I just wrote. So you paste it in, it's going to take a while. Okay, now it is assembled. So what I'll do is I'm going to go to the assemble view. This is the assemble tab. So the assemble tab is actually quite useful because what it shows you is on line 1, in the case of the mnemonic of LDID with a 0, it translates to 2 bytes of opcode. One of these is an opcode, 6F is an opcode. In other words, the assembler is kind of like doing the job of a compiler, but in a much simpler form. It looks at the text LDI and then with a register D, and then it would translate that to the opcode of 6F. 6F is just the hexadecimal representation of 8 bits. And those individual 8 bits are in this case 0110, which is the 6, and then 1111 as the F. Okay? So now you go like, but what does that do? Well, 6F and then a 00. The 00 here is representing the constant of 0 here. So whatever this constant turns out to be, that's whatever the second byte is going to be. So now the question is, but what does it do? Okay, okay. So before we answer the question of what it does, I'm just going to answer the first question, which is the job. What is the job of an assembler? The job of an assembler is to save you time. Okay, because if you don't let the assembler do this job, then you'll be doing the job of trying to remember what 8-bit is going to do what in the processor. So the mnemonic is just to make it easier for us humans to write code at this level of programming. Yes, yes. So that's kind of what is happening. It is not a hash table. It is much easier. There's no hashing involved. It is just multiply with a certain number, and then that becomes the address in raw. There's no hashing algorithm. That is correct. It is also guaranteed to be, dare I say the word, bijective. That is a term that we use in CISP 440 to describe a function where it can go in both directions. Okay. But from this class perspective, we'll take a look at this and go like, okay, so this is the entire program. The RAM file tab, which is here, This gives you the actual content that you can download, and you can load this content into the RAM of the processor. In other words, the assemble view is really good for understanding how the mnemonics that you specify in the source tab translates into opcode, which are just a bunch of zeros and ones. Okay, but it doesn't really give the computer anything that it can download into the RAM component of your processor. The RAM file does. Okay, so when you go to the RAM file, then you can go to File. Okay, here's File, and then you go to Download, and you can download as a CSV or a TSV. It doesn't matter which one. I typically use CSV because I use TSVs for something else later on, so I would use CSV. And this is where it is helpful to configure your browser where it asks you for the file name. Okay, because otherwise, if you try to save the same file name again, it would just put parentheses and then a number inside the parentheses, which is really annoying to me. Okay, but I prefer to have some control over the file name of how it is saved. So I'm just going to call this file ex1, which is the name of the source file. And I remember which folder I save it to. So now I can go to the processor. Okay, so in order to run this program, this is what you need to do. I'm double checking to make sure I'm recording, and I am recording. So for those of you who are thinking, are we recording? Yes, we are. Yep. You can use any text editor to create the program. In other words, what I put into the quote unquote TTPASM file is nothing more just a plain text file. You can do that in Notepad. But there's a little bit of a problem with Notepad, especially when Windows is configured by default. It will hide the extension automatically, which means when you save the file as blah 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 dot ttpasm, it is actually blah 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 dot ttpasm dot txt. It automatically appends the extension of .txt as long as you do not change the default file type when you save it in Notepad. Okay, I can show you guys how to kind of get around that problem because eventually you need to get around that problem. Yes. You can use any file extension, because the tool that we use for assembling the program does not care about the extension of your file at all. So that means, unless you're turning in your assignment and I put a restriction of the extension has to be TTP-ASM, you can actually use any extension you want. Now, the reason why I want to enforce the extension to be TTP-ASM is I want to make sure people do not turn in their CSV file because I'm not going to read the CSV file and try to disassemble the program to find out what it is. Okay. Oh, by the way, disassemble means it is the opposite of assembling. You're looking at the zeros and one, and you're trying to reverse back to the assembly code. That is called disassembling. All right. So now we go here, we go to the processor thing, and this will also be in the uh, instruction of the lab today. So there's no need to kind of worry about, oh, so where do we get all these files? So in the instruction of today's lab, you will get the instruction of how to get the files and how to get it into Logisim and so on. All right, so now that we have Logisim, we're going to go to the RAM component, which is this thing here. How do we distinguish between the RAM and the ROM component? This is the RAM and this is the ROM component. What is the quickest and easiest way to distinguish the RAM from the ROM component? The D pin is, oh, LD? Yeah, well, okay. So generally speaking, the ROM has only 3 ports, but the RAM component has a bunch more. Okay, so that makes it kind of fairly easy to distinguish between the two. So here you can choose, okay, 2 options. You can choose to go to the assembler, okay, and go to the assemble view, and then just try to remember each one of these and hand type everything into RAM. You can do that, by the way, because you can right click here, go to edit content, and then it's going to pop up a window. I need to move that into your view. It's going to pop up a window like this, And you can hand type everything if you want to. Or you can also right click on the RAM component and just say load image, and then you tell it where to find the CSV file that I have just downloaded. In this case, it's called ex1.csv in my temp folder. Now, obviously, in Windows, it is typically in your downloads folder. Okay, so this is just me using Linux, and I tend to save files to the temp folder because nothing in the temp folders will survive a reboot, and I don't need these files to survive a reboot. All right. So now I have loaded the content into into the RAM of the processor. I can now start to execute the program. So are we kind of getting a general idea of how to write the code, how to convert your assembly language code into a machine code where the processor can actually understand, and then how to download that code and put it into the RAM component that eventually will have to contain the code in order to execute it. Yes. Hmm. Oh, okay. So that's an interesting question. Slightly out of scope for this class, but I can still answer the question. So the question is, how do we write an assembler? Um, you know, is it for this processor or for any processor? For a different design. Okay. So there's a short and long answer to that question. The short answer to that question is this assembler is open sourced. It is. It is a Google Sheet. And as such, there's no secret I can hide from people who are using it. So it is mostly done by formulae in the spreadsheet. So if you click on one of these things, you can see that this is the actual formula in the spreadsheet. Some of these are a little bit horrendous, okay, and some other ones are. This one is not too bad. So you can see how I use regular expression. And this is why it is kind of cool to use Google Sheets compared to Excel. Excel is great when you need something to be well presented. Okay, if you need to format something, like this has to be boldface, this has to be red in color, and so on and so forth. Excel is the program to do it. But if you need to do actual processing, Google Sheets actually gives you more functionality when it comes to actual processing of text and data. Okay, so anyway, so this is it. And also, there's a little bit of magic that goes into the app script here. So when you open up the app script um, portion of the assembler, you can actually see there's quite a bit of code here. So a lot of this code is actually some of the magic behind the scenes, but they're all open sourced, which means you get to see everything. Is that okay? There's also a description. If you go to the processor drive here, you can actually read a little bit of the assembler manual. And I encourage everybody to read at least a portion of this manual. And inside this manual there's a little description close to the end that talks about the implementation of the assembler. So for people who are curious about how to develop an assembler using a spreadsheet, which is not usually the right tool for the job, but it can be done. It's just like you can use. Okay, I'm not going to talk about it because I can probably go on a really long tangent with that one, so I will refrain from doing that. But anyway, the implementation is a description of what each column does in the assemble view, and that really does most of the heavy lifting for the assembler. All right. Any other questions? Okay, so that's a little, digression from what I really wanted to talk about, but it's okay. It's not a bad digression. So now getting back to Logisim. Now we are ready to run the program. So now you guys, we all have to focus now, okay? Because this is the actual description of how the code that is stored in RAM is going to be quote unquote executed. How do we get those bytes and then have the processor to perform a specific operation based on the content of RAM? So That's really kind of the focus of today's lecture. Okay, what I have just done up to this point is more or less kind of like a bird's eye view of the whole thing. Gives you kind of like a general sense of what is this tool, how does it relate to the processor, and just how do we write code? What are we going to do for the rest of the semester? But now we're going to focus. Okay, now we're going to focus on how instructions execute. So this is the part where you might want to take notes or at least note the time when I start to talk about a specific thing. When you try to analyze how a program executes, you have to start with the microcode pointer. Just like every other register, the microcode pointer is reset to 0 as its default value. So when you reset the processor, when you do a control R, every register resets to 0, including the microcode pointer. The microcode pointer is also the only register that updates or increment, most of the time increments, when we have a falling edge. All of the other registers will update on the rising edge. The microcode pointer is the only one that updates on the falling edge. So this is the starting point. So when you look at this, okay, it has a content of 000 because I just restarted the whole processor. And this goes into ROM, okay, the only ROM in the architecture. And it is addressing location 000 because the A port connects to the output of the microcode pointer, which has the content of 000. Every digit that you see in the microcode pointer and also on the left edge of the content inside the ROM, they are all in hexadecimal. Are we doing okay so far? Is everybody convinced that there's a reason why location 000 of the ROM is addressed because it is highlighted? Okay, there's no way to turn off this ROM because select is always connected to a one, to a constant of one. So that means the output, which is the D port of this particular ROM, is going to be reflecting the actual content of location 000 of the ROM. So ignore the part to the right-hand side of the slash. The part to the left-hand side of the slash is the binary representation of 1080007 as a hexadecimal number. Are we still doing okay so far? Yep, go ahead. It is hard coded, yes. So it is hard coded in the ROM because that is called the microcode. Okay, so whatever you see in the ROM is called the microcode of a processor. And that's why whatever is specifying the address of the ROM is called the microcode pointer because it says, oh, pay attention to this particular specific microcode. Yes, not yet. Not yet. Okay. Eventually, yes, but not yet. Okay. Mm, So not yet. Okay. The only thing we know about the microcode pointer is it tells us which address or which content, what location in the ROM should be outputting all of these, all of these 20, I think 26 bits. And these 28, 26 bits go to, basically everywhere in the processor. Particularly, it would go to the enable of registers. It would go to the select of multiplexers. It would go to the select of demultiplexers and so on. Okay, in other words, it's trying to figure out we need output from this register connected through this switch and then connected through that switch and so on and blah 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 and eventually to whatever destination the register output is supposed to connect to. It's basically doing the job of routing and also the job of enabling the correct components in order to get a specific thing done. All right, so shall we move on? Any other questions? Yes, go ahead. It does not always increment, but we'll see when it does not just increment. Okay, we'll get to that point and it will say, oh, okay, this is not just incrementing. Why is it not incrementing? So we'll explain that when we get to that point. So this part we have analyzed from last Thursday. Okay, so last Thursday we have done a little bit of analysis of what it does at location 000. And I also said very specifically this is called fetch. Okay, this is called the fetch phase of the cycle of executing an instruction. So that is important. Okay, so you probably, hopefully, have written that down from last Thursday already. Because if you have not, then you probably should write it down now. Okay, so we already know from last Thursday that RAM is active because we can see how RAM select is a green line here. So this green line or RAM cell really is just one of the output pins of the ROM. At the D port, in fact, it is bit 1 of the output of RAM, of the data port of RAM. Yes, yes. So, yep. Well, it is kind of like a portal. Okay, if you play the game Portal, this is like a portal. So basically, this is in Logisim is called a tunnel. It's called a tunnel because anything that has the same name, any tunnel that has the same name of RAM cell, they are logically connected. So you can see there's also RAM cell here. So these two are logically connected. The reason why I use a lot of tunnels in this case is twofolded. One is I don't want to run wires all over the place, okay, because that's just going to look really ugly. Two is I want to be able to label what that wire is about. So using a tunnel gives me solves two problems at once because now I can name the tunnel in a way that describes, oh, this is the select of RAM. Yep. Huh? What about those? Right. You can end up well, okay, so logically in Logisim you can have flyover without much restriction, but it would make the circuit very difficult to read. Yes. hmm So if you're actually designing a processor, I'm assuming you want to design it in silicon instead of using discrete components. So if you want to use discrete components on an actual circuit board, that's going to be quite a bit of work because the routing of the actual connection, if you use wire wrapping, then you can cross over any way you want because you're basically making direct connection between between the points. But if you are doing this on a printed circuit board, then you are limited by the routing resources on a printed circuit board because you cannot cross over indefinitely. There's a certain limit that you're going to hit where, oh, I cannot route this signal from this pin to this pin anymore because it's going to cut across some wire, no matter what you do. Yep. So from our perspective is from a logical perspective. So we are not really concerned about the actual routing of the wires. hmm All right. So last time we already talked about this, how the address port is eventually connected to the program counter. We also noticed how the D port is eventually connected to the instruction register, which is enabled at this point. You can see how the instruction register is enabled. So one thing you need to remember is this is called the fetch phase of instruction execution, and it does one thing. Okay, so I'm going to describe that one thing with RTL. Okay, I'll explain what that is. So I'm going to start up my mouse pad here. Okay, so I'm going to write this down, okay, which means you probably want to make a note of that at some point, okay? So when the microcode pointer equals to 000 in hexadecimal, and we are having a rising edge, okay, this is called the fetch phase of execution instruction. And the way I would describe it is the instruction register getting whatever the program counter is pointing to. So this is, it looks like C code, but it is also called RTL. Okay, RTL stands for Register Transfer Language. So I'll say that one more time. RTL stands for Register Transfer Language. And what it does, okay, is to describe the internal working of a processor in terms of, oh, what is this register doing in the context of this particular operation? In this case, the program counter is acting as a pointer into RAM. And that's why it is dereferenced. That's why we put an asterisk right before PC. Okay, but it is on the right-hand side of an assignment operation. So that means whatever the program counter is pointing to in RAM is providing the value to update whatever is on the left-hand side of the assignment. So the instruction register is the one getting updated by the content that the program counter is pointing to. That is the objective of the fetch phase of instruction execution. Yes. Register transfer language. Now we'll see that, okay? We'll see that again, okay? Because I describe every instruction using RTL as well, and there's a document that maps every instruction to the equivalent RTL. So we'll get to that too. All right. So with that said, because we already did this on last Thursday, I'm going to just go to the edge transition. So I'm going to make a clock here. Control T, if I remember correctly, if you go to simulate, you can do a tick once. It is Control T. So what Control T as a shortcut does, all it does is to toggle the state of the clock pin. Like this clock and this clock, they're all the same clock. They're basically the same tunnel. Remember the concept of a tunnel? All the tunnels that have exactly the same identifier, they are logically connected. Okay, so when we have a when we have a rising edge on the clock, then the instruction register will update its value based on whatever is presented to its own D port. But we know this D port is connected at this point to the D port of RAM, which is specified for reading. So the D port of RAM is in output mode. So when we have a rising edge, then it is going to store whatever is at location 00, which is specified by the program counter, which has a content of 6F. So this 6F will now be stored in the instruction register when I have a rising edge. Do we have any questions about that? Yes. Yes, RAM contains the entire program, but it will also contain what we need to store the data, like the variables. But in this class, we are far more concerned about the program itself. So we'll focus our discussion on the content, on the instructions. It contains the opcode that represents the program. Mhm. All right. Any other questions? Okay. So I'm actually combining what we already talked about last Thursday to today's lecture. Okay, so that's why it is really important to make sure that you kind of review the material from a previous lecture before going to the next lecture. Okay, it is really, really important. All right, so here comes the Control T, and you can see how the instruction register is now storing the opcode of 6F. So are we good so far? All right. So now we are ready to have a falling edge. None of the registers is going to respond to a falling edge except for the microcode pointer. So now we have to ask the question, how is the microcode pointer going to update itself? Because it's going to experience a falling edge and it is always enabled. So the enable line is connected to a constant of 1. The microcode pointer is always enabled, which means for every falling edge, it is going to update. The question is, what are you using to update the microcode pointer? So how do we answer that question? Okay, so how? Yep. Exactly. So this is important, okay? How we answer that question is important. What mental process you go through to try to answer that question is important. Because the question was, we know the microcode pointer is about to update because it is enabled and the clock is about to go from 1 to 0. It's about to have a falling edge. And because of how the microcode pointer is configured, it updates on the falling edge. So we know it's going to update. So the natural question or whatever is it's natural to me. The question to ask is how is it going to get updated? Who is providing the value to update it? So this line of thinking, there's no specific. I'm sure some scholar has a name for this. I just call it dependency-based thinking. Okay, what does it depend on in to determine how it is going to be updated? Okay, so we look at the D port. Okay, so we follow the D port. Okay, which is also something that we did, something like this we did on the other day. So the D port is the output of a multiplexer. So now we go like, okay, so how is the multiplexer going to specify its own output? So now you have to think about dependency again, right? What determines the output of a multiplexer? Yes. Yep. Yep. And on top of the selector, also, whatever input it is selecting, we need to track that one down. So the select is under the gray dot, which now is a 1. So that means input 1 is connecting to the output. So what should I track down next? Input 1. Very good. Okay. So now we track down input 1, which is here, and it connects to an adder. Okay. This C in C out thing is an adder. Okay. So what it is doing is the top port is K0, the left top port is X, the lower left port is Y. Okay, I'm using the terms that we are familiar with based on how we describe binary addition. Okay, C out is essentially K8 in this case. It's not used. And that's why you don't see C out connected to anything because we are not using it for anything. The wire that is actually highlighted right now, that's our sum. That's our S row in the way that we described binary addition. So essentially what it's doing is it is adding the microcode pointer, the current value of the microcode pointer, and 1, and then outputting that value back to update the microcode pointer. Okay, so at this point, it is just incrementing. Do we have any questions about that particular analysis? Yes. You mean multiplexer? Well, we'll see. We will actually see that. Okay. So right now it is just incrementing. Yep. Yep. That is correct. All right. So are we ready to look at the microcode pointer and just watch it go from 000 to 001? All right. Control T on the keyboard, and there we go. Okay. So now we are back. We're about to have another rising edge, which means we don't have to look at the microcode pointer for the time being because the microcode pointer does not update on a rising edge. It updates only on a falling edge. But all the other things, RAM, all the other registers, they all update on a rising edge. So now we have to go figure out what is going to be affected again, right? But if you remember, it is amazing that I actually remember I remember what I said on last Thursday. There are only a few things that can be enabled or can do something that is actually of consequence. One would be the register bank. Okay. Now, the register bank itself is no more than just a bunch of registers like this. And they have a specific way to connect to some output pins, and the input pin has a specific way of connecting to the registers. But at the end of the day, It is just a bunch of registers that software your code has direct control over. Okay. In other words, you can specify with this instruction, I want to update this register, or I want to use the output of this register to do blah, blah, blah. Okay. So these are software addressable registers that's inside the register bank. Okay. And we don't see anything being enabled here. Okay. So that means we can kind of ignore the register bank for the time being. In other words, all we are really doing is to focus on things that are bright green, that are enabled. So we have to analyze this. Nothing is really happening. We look at RAM. Should I look at RAM and see what it is doing this time? No, because it is not selected. Okay, so if RAM is not selected, it's not it's not outputting anything at the D port, and it's not updating its own content either, because it's neither reading nor writing. It's just chilling, right? It's just going like I'm just taking a nap here. Okay, so the RAM is taking a nap. We go like, okay, fine. We don't need to track down what the RAM is doing. So we look at some of the other registers that we have seen already. We have the instruction register. Do you think the instruction register is going to do anything useful here? No, no, it's not enabled. Okay, so we can go like, okay, fine, it's not enabled. So now we go like, there's only one more register. So there's the register bank, there's RAM, the instruction register, and there's one more register that we need to look at. It is the program counter. So the program counter is over here. You go like, oh, okay, the program counter has PCEN, program counter enable, is a 1. So the program counter is about to update. So what is the next question to ask again? What is going to the D port of the program counter, right? So now we try to track that down. So we try to track that down. Okay, we look at this wire. It's coming out of a multiplexer, kind of like the microcode pointer. And the select is a dark green, which means it's a 0. So now we have to track down input 0 and see where it's coming from. Oh, it's coming from another adder. Okay, this adder is doing about the same thing as what the other adder is doing, except whether it's incrementing or not is controlled by PC Inc and ADDR mux. ADDR mux is a 1, PC Inc is a 1, so that means 1 or 1 is a 1. So yes, we are going to add 1 to whatever program counter has, and then use that to update the program counter itself. Is that okay? In other words, once you have fetched the opcode from RAM from a location of RAM, I don't need the program counter to point to the same location anymore. I'm advancing the program counter so it points to the next opcode that I need. Because the current opcode, the one that I need to execute, already has a copy stored in the instruction register. So now it is time for me to, okay, let's just auto increment the program counter so that it doesn't point to the same location. Does that make sense? The micro pointer is at 001 right now. And it's because of the content in the ROM at location 001 that we have rerouted things in the processor. So we are no longer saying, oh, we want to read from RAM, and then the data port goes to the instruction register, and we want to update the instruction register. This time, it's rerouting things. It's going like, oh, we just want to update the program counter and increment it. Exactly. Yep. Yep. Exactly. Yep. 6F? Well, we'll see. We'll see. Okay, that becomes important later. Okay, I really like the curiosity. Okay, because it helps to drive the class. So that's good. That's all good. So now, on the rising edge, all we will see is to see the program counter incrementing. So here's Control T. All right, big surprise. Okay, it increments to 0, 1 from 0, 0. So in terms of the execution cycle, some people can say, oh, okay, the auto increment of the program counter, this is a post increment, is a part of the fetch cycle. Okay, some people see it that way, some people do not. It doesn't really matter. Okay, is that okay? Let me just check. Does everybody understand the differentiation between a pre-increment versus a post-increment in C++? Okay, I see nods. Okay, very good. So I think it is safe to say for those people who are not nodding and not really understanding the differentiation between pre-increment versus post-increment, what should those people do? Okay, that's a very pragmatic answer. Or you can go to ChatGPT, explain the differences between a pre-increment versus a post-increment operation in C++. I was expecting someone who's going to give a much harsher remark like, go back and take CISP 360 again. Oh, yeah. Oh, okay. Okay. Uh-huh. So this time, okay, when we are about to have a falling edge, this time is going to be fun, right? Because when we have a falling edge, the microcool pointer is the only thing that's going to update. Then we have to track down the D port of the microcool pointer. It connects to the multiplexer, but this time the multiplexer has a select of 0. Okay, because you can see this is dark green. And by the way, why does it have a dark green this time? So you tracked it down. Yes, go ahead. Because it is bit 24 of the output of the ROM, it is just programmed to be like that. Okay? In other words, the content of the ROM is what is the actual puppet master, if you want to see it that way, that is controlling everything else. Okay? You should increment, you should stay put, you should update. And this switch, the output should connect to input one, and so on. So the ROM, the content of the ROM contains quote unquote the script for the puppet master. Okay, at any given time, the puppet master is going to output the content of one location of the ROM, and therefore configuring all the other components so that they can work together to get one simple operation completed. Yes. Yes, and we'll see that how it jumps. Okay, so we're going to see how it is going to perform an indexed jump. Okay, so it's not just a jump; it is called an indexed jump. Correct. Yep. But now that we know why this multiplexer has a select of 0, we now track down input 0. So now the question is, what is this? Okay, what is this thing here? The first thing is, okay, instruction is just a tunnel. Okay, instruction is a tunnel that is the output of the instruction register, which is our 6F. Okay, so after that, we're going to focus on the splitter or the merger because it is in the opposite direction. So we now look at the merger. Okay, and I'm going to focus a little bit in a little bit because it's harder to see if it is all zoomed all the way out. So now I think it should be fairly clear. So you can see that for this particular splitter, bit 0 to 3 comes from this particular wire, and it is connected to a constant of a 4-bit 0. Is that okay? Now, how do we know it is a 4-bit 0 instead of a 2-bit 0 or a 3-bit 0? Because the splitter says that wire corresponds to which range of bits? 0 to 3. 0, 1, 2, 3. 4 bits. Okay? So now the next question is, what about the other wire of the splitter for bit 4 to 11? From bit 4 to 11, it is copying from the instruction tunnel. But we already know the instruction tunnel is really just the output of the instruction register, which contains the, the content of the byte that we just fetched. Okay, say again? That came from RAM. Exactly. It came from RAM where the program counter was pointing to. Okay, I said was because the program counter has incremented already at this point. Okay, so What do you think is going to end up in microcode pointer on the falling edge? We know 6F is somewhere, but there's an extra zero. So now the question is, are we looking at 0 6F or 6F 0? If you're saying 0 6F, that 0 would correspond to bit 12. No, I take it back. It would correspond to bit 8 to 11. Because when we read a number, the most significant digits are on the left-hand side. It'll be 6F0. That is correct. Now, how do we know for sure this is going to be 6F0? All you have to do is to use the poking tool and click on this wire. You go like, but Tack, you just lied. I don't see 6F0 here. Well, that's because you need to convert the base 2 representation back into base 16 representation, hexadecimal. So now we see 0110, and somebody's going to take a picture of me pointing this way and go like, Tech, you're doing a salute. Bad. No, I'm using a finger. Okay, so 0110 is a 6, 1111 is an F, 0000 is a 0. So we have 6F0. This is how the opcode that we store in RAM directly relate to what location of ROM we are going to get into. Yes. Say again? That is the decimal representation of the same bit pattern. And you can program Logisim to use base 10 or base 2 or base 8 representation. So you can change that. All right. So are there any questions about this point here? So that means but once we have a falling edge, we are expecting the microcode pointer to go from 001 to 6F0. Okay, so let's go ahead and check that out. Okay, we'll get it to happen. Control T again, like so, and it becomes 6F0. All right, so this part is important, okay? This part is also important because it is called the decode phase of instruction execution. And I will put this into my little notepad here. You should probably do something similar, okay? When the microcode pointer is 001 and we have a falling edge, this is called the decode phase of instruction execution. And the way it's going to be represented is the microcode pointer is getting the instruction register left shifted by 4 bits. Hmm? Um, yes, because I was way overestimating how many locations I need to implement one single opcode. I could have gotten away with only 2 locations. It's just me trying to be safe. It's like, oh, okay, I'm gonna save like 16 locations for the microcode to implement one single opcode. But as it turns out, I really only needed 2 instructions for every opcode that I wanted to implement. Okay, do you guys have any question? Because we have been kind of like doing this almost for the whole class. Do you want me to answer one of your questions? Hmm? You're good? Okay. All right. So that is important, okay? Because when we decode an instruction, that is when we get to the instruction or opcode specific location in the ROM. Yes, it is consistent with how this processor works. But we don't always use 4. As I said, I way overestimated how many locations I need in the ROM to implement one opcode. Yeah, sure. Go ahead. Hmm. Okay. So the RAM, the content in RAM is more like a macro. Each location is more like a macro, and so that you don't have to specify in full date details in your own program what's happening, what is the connectivity between the components inside the processor. So every opcode is like a macro. It's just like, oh, okay, this is macro ABC. Oh, what does it entail? Well, we look up the ROM and then the ROM, the 16 locations in the ROM corresponding to that one opcode. That gives you the space to implement that macro using, detailed operations. In the sense that we're specifying which register goes where and which register is updated how and so on. So so to answer the question of whether all processors are the same, the answer is no. Okay. The way I chose the opcode is somewhat arbitrary. Okay, there's a certain systematic way to doing it, but otherwise, it also has a somewhat arbitrary, component to it. So when you look at processors that are what we call binary compatible, then it means regardless of how the microcode is implemented, the opcodes are the same. The same opcode specifies exactly the same operation. That's when you have binary compatibility. So between Intel processors and AMD processors, they are called binary compatible because the same executable it will run on either an AMD processor or an Intel processor. Yeah. So when you're looking at different architectures, like the ARM, the entire family of ARM architectures is different from the family of x86 architecture. So they would not share the same opcode. Now, does it mean that they cannot have the same opcode? No, they can have the same opcode, but what the opcode does can be drastically different. Yep. Operation code, it is the content that we store in RAM that in return is translated to a location in the ROM. And the content of the ROM now specifies exactly what we need to do for that specific opcode. So right now, let me zoom back out a little bit. So right now, you can see the ROM is addressing location 6F0. This particular bit pattern is specific to the LDI instruction using register D as the register. Is that okay? So this is specific. So now we want to say, okay, but what does it do? Yes, go ahead. Yes, this is the very first instruction of the program that we did. Yes, the first line. Yep, go ahead. It's more like a function pointer, it's more like a function pointer in an array of function pointers. And the opcode is the index into the array of function pointers. I don't think that would be a good analogy. I can write a C code thing to represent, the actual context of what the opcode really is. But I don't want to do it now, okay, because we are really in the middle of tracking down what 6F actually ends up doing. So now we go through the same analysis again. So this is a good time to introduce a suggestion, which is to get a colored pencil or highlighter, okay? Highlight the instruction register. It's one of the things that you should look at when you try to analyze what an instruction does. And then next, you want to highlight the RAM component, which is another component that can actually do something. The third one you need to highlight is going to be um, the program counter. Okay. And then the last one that you can highlight if you want to is the instruction register. The instruction register, for the most part, is not really useful when you're executing an actual opcode. It is only useful when we are fetching the opcode. But when you're actually executing an opcode, when you're in the execution phase of an instruction execution cycle, the instruction register is useless. Okay, so you really only have a few things that you have to focus on when you try to analyze what is this opcode actually doing. Okay, so now we look at all this thing here, and for the first time, hey, this is a bright green. It something inside the register bank is going to update. So what do? We look into it. Okay, so you can right click and then go to View Register Bank, and now you can actually get to see the entire thing. So we have one component that I have not explained, which is this one here. It is called a decoder. But the easy way to look at a decoder is it is basically a demultiplexer where the input is a constant one. Let me say that one more time. It is the same thing as a demultiplexer where the input is a constant one. In other words, all you can do is to direct where that one is going in which one of the four, which one of the output is going to have that one. Is that okay? So it's called a decoder, but it really is just a deformed um, demultiplexer. So now we look at the decoder. Okay, the decoder has its enable. It is enabled. Okay, this is the enable of the decoder. It is enabled, and this is once again the select. And you can see the select goes to register input select, which is 1 1. And that's why output 3, which is corresponding to binary 1 1, is the only one that has a green wire, a bright green wire. Everything else have dark green wires. Yep. Huh? This one? So you can go to the appearance view, and then you can click this. It comes from incel, because when you click on this, it will show you in the picture, what input pin it's corresponding to. Yeah, so it's coming from this RISEL, which is register input select. Yes. So you can actually, highlight it. Okay, it's inside, the thing. But if you were to highlight it, it would come from the data port of ROM. So it would be two of the bits of the output port of ROM. Yep. All right, so getting back into the register bank. All right, so now the question is, we know register D is going to update because it is now enabled. And the question now is, what are we using to update register D? Does that make sense? So this is the line of reasoning, and I think it is important um, to understand the process and not what the instruction ends up doing. Okay, because if you understand the process, you can reapply the process to a different instruction and go like, oh, this is an instruction that tech never talked about, but I can reapply the process so that I can understand what that opcode is going to do. Yep. Why is it? Oh, this one? Because it is an input pin. It's an input pin that on the outside at the processor level connects to the actual clock signal. It's not. It's more like a parameter. If you look at a circuit like a function, this is all of these pins, all the input pins and output pins, are parameters of the function. Does that make sense? Okay. So now we track down this wire and we go like, oh, okay, it's just coming from register input. And if you look at the packaging, all that really is corresponding to is this pin over here. So now we go back out to the main circuit and we ask, oh, okay, so it's corresponding to this wire. It's coming from a multiplexer again. So the first question in this case is whether the multiplexer is even enabled, because unlike the other two multiplexers that we have seen, this one does have an enable pin. So if it has an enable pin, you have to first determine whether the multiplexer is even enabled. But it is in this case. Okay. So now you ask a question of how are we selecting the input? The input select is a dark green, which means input 0 connects to the output, which means our next step is to analyze what is going into input 0 here. So you can see that, oh, this goes all over the place. This is a nightmare. Well, it's not, okay? It is not that much of a nightmare because this is an input port. This is an input port too. An input port cannot specify content on a wire. So we know that this particular connection here is not going to specify the content on this wire. So we go like, oh, maybe it's this one here because this is the output of a demultiplexer, except the demultiplexer is actually off right now. So this demultiplexer cannot specify the content either. And this is also the reason why we have to go through the um, labs that basically just have you guys to go through the nightmarish questions of, oh, this is the sequence of configuration, what does it actually do, what output or what is the result that matches this sequence of operation. This is why we have that lab. Okay, is so that you guys understand how multiplexers and demultiplexers operate by themselves. Okay, then you can understand how they work together in order to get the processor to do what the processor needs to do. Okay, so the next connection point is right here. It is connecting to the input of the instruction register. Once again, that cannot specify the content, so it is a dead end. So now we go to the right-hand side. Eventually, we go like, oh, it's going to the D port of RAM. Now, with the D port of RAM, it can be an input or an output. So now we have to first ask the question, is RAM even being selected right now? It is, okay. Are we reading from RAM or are we writing to RAM? We are reading because LD is a 1. Okay, great. So now we know the output or the D port of RAM connects to the D port of register D inside the register bank, right? We know RAM is being selected. We are reading from RAM. All is good. What is the next question? Which location, right? So the location in RAM is specified simply by the A port. But then the next question is who is specifying the content of A port? Okay. So are we all kind of getting the chain of reasoning? Because I want you guys to do this kind of chain of reasoning to instructions that I am not going to explain. Yep. Yep, essentially. So it only looks horrendous to begin with because there's so many components. But once you figure out that, oh, okay, we only have to really pay attention to the register bank, to RAM, and to the program counter for the most part. How many components are we looking at? There's only three. Okay. Is it really difficult to go through three components and see any one of those things is being active? Nope. Huh? Well, I mean, it's not that bad. Okay. It's not that bad. Okay, so now we can see this wire is coming out of a multiplexer. This multiplexer has no enable, so now we just focus on the select. It is a bright green, which means input 1 connects to this output. So now we track down input 1 of this multiplexer, and that, guess what? It comes from the program counter. Yep, yep, yes, yep. And this is also why, and because we can have so many components connected to the same wire, but at any time, up to one of them can be specifying the content of that wire. This is why we sometimes need to have a disable so that if you have multiple things that can potentially output to the same wire, we have to tell everybody except one to shut up. Correct. Yep, exactly. Yep, go ahead. Say it again. Oh, this is exactly it. Okay. So this is exactly it. So what I'll do is I'm going back to the register bank here, and register D already had the content of 00. So changing 00 to 00 is no fun. So we're going to change it. So we'll change the register D. I'm just injecting an initial value of AB. Okay. For no particular reason. Okay. I'm just injecting a value of AB here. So we are okay. So the analysis is essentially done, okay? Because we now know that the program counter is specifying the address port of RAM. The data port of RAM is um, going to the D port of register D. Register D is enabled. It's about to get updated. There's only one more thing. The program counter is also enabled. So that means the program counter itself is about to update as well. Okay. And how is the program counter going to update? So you track down the D port. It comes from the multiplexer. The multiplexer has a dark green, has a 0 as the select. It comes from an input 0. Input 0 of the multiplexer comes from the adder. The adder is adding a 1 to the program counter. So that means the program counter is also going to increment. So it would seem like we are pulling the rug under ourselves, but that is not true. It is not true because of propagational delay. Because in order for the program counter to update its output based on the updated input, it takes a little bit of time. But the program counter, the current content of the program counter, is already connected to the A port of RAM. So the A port of RAM is not going to see the actual update of the program counter because it takes propagational delay for that change to become effective. Okay, so the actual change here is the program counter would change from 01 to 02, and inside the register bank, register D would become 00. So I think that answers your question of an example where a register in the register bank is going to get updated. Uh-huh. To the main circuit. Uh-huh. Yes. But right now it is specifying location 01, and that's why location 01 is the one addressed. Then it will be 60. Yep. Yep. Whatever register that is enabled. All right. So, yep, correct. Yep. Yep. Go ahead. Oh, sorry. hmm So the 00 is coming from RAM itself. It has to do with how we specified the LDI instruction. If we had, if we were to say LDI D and then the 4, this would have been 04. 6F would still be the same. Correct. It is specific to the register. Yep. Yes, go ahead. Yes. All registers update on the rising edge except for the microcode pointer. So let me see what time it is. Okay, we still got a few minutes. We can finish this. So what we want to focus on now is to watch how program counter changes from 01 to 02. And register D is actually presented here as well. So right now, register D has 1010, which is A, 1011, which is a B, and we will see this turn into 00, all zeros. Is that okay? So there are two things being updated in this particular rising edge, register D and also the program counter. Okay, so here we go. Control T, register D got zeroed out, and then the program counter got incremented to 02. So going back to the description of things, so LDID something, okay, whatever that is, the RTL description is register D is updated by the program counter, whatever the program counter is dereferencing to, but then the program counter is also post incremented at the same time. So this would be the RTL description. This is the RTL description of LDID and then blah blah. That blah blah is whatever the blah blah is the byte that is following the 6F. The assembler is the one that puts it over there. So getting back to, how do we, if you cannot remember everything that I said today, what are we going to do? I do not expect everybody or anyone to remember everything that I said. That's also why we have a recording. But there's also a file here called the opcode table. There we go. So the opcode table has 4 columns. So we'll focus on the one that we are talking about today, which is the LDI instruction. It is row 19. Column A is the binary code. Okay, so column A specifies the binary code. 0110 is our 6. And then we have 11XX here. XX is specifying which register is going to be used as X in the mnemonic. Because we specify D as X, so register D has a bit pattern of 1, 1 in this case. Now, how do we know that? Because at the beginning of this entire document, it explains how register A is 0, 0, register B is 0, 1, and so on. So if we specify register D, then the XX is going to be 1, 1. And that's why we have 6F as the opcode. Okay, because the constant part is 0110, which is the 6, and then 11 is also constant. But the other 211 represents register D. That's column A. So column A is the binary opcode. Column B is the mnemonic. Okay, this is the symbolic name to make things easier for us. Let me finish this and then I'll address your question. Column C is the RTL description of what the instruction does. And then column D is really just a verbal description of the instruction. So in the case of row 19, it is loading a constant value right after the opcode into a certain register. And I can now address your question. Yes. So in this case, whatever the program counter to, no, only this one has a slash slash. It is just an alternative way of looking at the instruction. Yep. All right. So I will give you guys the access code for today's lab. So you guys are going to go through the whole process of assembling and getting a program to run in Logisim today. And it is called this one. It is familiarizing with the TTP tool chain. And then the access code is TTPASM or in uppercase. I'll see you all at the lab.